Hello students, in previous video we have studied about total internal reflection, what is the phenomena and what are the necessary conditions for TIR. Now in this video we are going to study about its applications. So there are four major applications that we have to study. First is the sparkling of diamond, which is because of the phenomena of TIR. Second, we have Mirage Formation. Third is the totally reflecting prism. And the last one is optical fiber. So these are the four applications of total internal reflection that we are going to study today. First, I am starting with the sparkling of diamond, which happens because of the phenomena of TIR. So diamond is an allotrope of carbon, and the refractive index of diamond, if we talk about its refractive index, it is very large. Diamond has a very large refractive index, and since we have proved that the refractive index is inversely proportional to the critical angle, as we know the relation mu is equal to 1 upon sine IC, where IC is the critical angle and mu is the refractive index. So diamond has a large refractive index, and because of that its angle of incidence, means its critical angle, is very small, and its value is about approximately, it is about 24.4 degrees, right? So this is a very small angle, and the faces of diamond are cut such that the light entering the crystal suffer TIR repeatedly. Okay, since we know that diamond is cut into different faces like this, we cut it into different faces. So these cuts that we make on the surface of diamond, these are made such that once the light enter the crystal, it suffer TIR repeatedly, and because of that it get collected inside and comes out only through a few faces, and that is the reason diamond sparkles when we see in the direction of emerging light. Okay, so the reason is diamond is cut such that light that enter inside it, light enters it, show total internal reflection and get collected inside, and come out of it through some faces, not from all the faces but by some faces, and because of that it appear lustrous to us. Okay, because of these TIR, total internal reflections, that those light rays show repeatedly, the diamond sparkles and appear lustrous to us. So this is the first application of total internal reflection in our daily life. Now the second application is the mirage formation. Now this happens to the areas where temperature is high. Now what happen in this, suppose we are traveling on a hot summer day, it is a hot summer day and we are traveling, temperature is quite high, then the layers of air or atmosphere, suppose this is road and we are traveling on it, so the layers of atmosphere or air which are near to the surface are rare. Okay, these are rare because their temperature is high, while as we go up the density of air becomes high, or the air get colder, or we can say denser. Means as we go up or away from the road, the temperature reduces, and this colder air is comparatively denser to the, in comparison to the this hot air, which is rare. So whenever there is some plant or some building or some object here like this, so the rays that are coming from this object are actually coming from denser to rarer medium. So that's why they actually bend away from the normal like this at every layer. Okay, they bend away from the normal at every layer, and there exists a certain point where they actually bend, or we get an angle there, a stage we reach there where angle of incidence becomes greater than the critical angle, and these rays get reflected to the person who is observing that object. So the person is observing from here to this object, but the light rays coming are, these are coming like this, so they appear to come from this point. Okay, although these rays are coming from this tree, and since it is moving from denser to rarer medium, so they go away from the normal, and at a certain point the angle of incidence is greater than the critical angle, so they bounce back to the same portion. That means the area of the denser air where we are observing from the observer point, when we see this, it appear to be coming from this location. So actually the tree is here, but we can see its image or its reflection at this point. Now this is called mirage formation, or we can say it is a delusion. It is an optical illusion observed in deserts or the surfaces which are quite at high temperature or which are hot, and because of that a traveler can see a shimmering pond of water. Means this reflection appear to us like a shimmering pond of water from some distance, but when we come forward towards it, we can't see that. It's not like that, it was just an illusion. So this is called mirage formation. We can define it as an optical illusion in deserts. It usually happen in deserts, or normally in our regions whenever the temperature is quite high, like in summers when the temperature is around 50 degrees Celsius, then we can see it sometimes on open roads. So an optical illusion in deserts or over hot extended surfaces due to which a traveler can see a shimmering pond of water some distance ahead. And this is because of the surrounding objects. It can be a tree or some other object that appear inverted to the person actually, but that person think like that there is a pond which actually disappear because it was only appearing when you were at this position. When you move ahead, this angle symmetry get lost, and then in that case this angle of incidence is not, maybe or maybe not, is greater than critical angle, and then you will not be able to see that reflection of the tree and it disappears. So this is called mirage formation. Now the next two examples we have to study are totally reflecting prism and optical fiber. So I am starting with totally reflecting prism first. So first of all, I am starting from the question, what is a reflecting or totally reflecting prism? So it is a right angled isosceles prism, right? This side, these sides should be equal and this angle should be 90 degree. Means it is a right angle isosceles prism then we call it as a totally reflecting prism. Since these two sides are equal, then these two opposite angles are also equal, and these are equal to 45 degree each. So this is the formation or description of totally reflecting prism. Right angled isosceles prism, or we can write it as a 45 degree, 90 degree and 45 degree prism is called totally reflecting prism. This is the formation of totally reflecting prism. Next point that we have to note about this prism is whenever a ray falls normally on any face, like this, normally on any face or on this face, then it is incident on the inside face at 45 degree. Means this is the inside face. On inside face it will be at 45 degree, that is at an angle greater than the critical angle for glass, because for glass the critical angle is 42 degree, and that is the reason the ray entering, which is incidenting here at 45 degree, shows total internal reflection, and that's why we call it as a totally reflecting prism, because it shows total internal reflection. So the thing is, whenever a ray falls normal, right, normal means at 90 degree like this, to any face of this prism, it is incident at 45 degree on inside face. Now this significance of 45 degree is कि this angle 45 degree is greater than the critical angle for glass. For glass the critical angle is 42 degree and the value of angle we have is 45 degree. Means the ray which is incidenting on this surface at 45 degree will undergo total internal reflection instead of refraction. Hence the ray show total internal reflection. Now this property of these prisms can be used in three ways. Okay, it can be used in three ways. The first way in which we can use this property of total internal reflection of this prism is it can be used to deviate a ray through 90 degree. Means if we put this prism in the path of a ray of light, it will get deviated through 90 degree. So it will happen like this. If a ray is here, okay, it is coming normally to this plane, then on this surface it will be incident at an angle 45 degree, which is more than the critical angle. That's why this ray will not pass into the air, but it get totally reflected inside the prism like this. Now this ray that we are getting, this is along the normal of this face, and it will go undeviated like this. That means the ray is coming in horizontally and we are getting it vertically. Now there is a deviation of 90 degree between the incident and the emergent ray. So that's how we can deviate a ray by 90 degree using this prism. Second use of it is we can invert an image by the deviation of rays through 180 degree. So it can also deviate a ray through 180 degree, due to which we can get an inverted image. So the application is to invert an image with deviation of rays by 180 degree. Let's see. So suppose we have an object AB and light rays are going from this, like from this object like this. Then here it is making an angle of 45 degree at these both points, and instead of passing to the air or coming out of the prism, they will bend down and show total internal reflection again at these faces, they will form an angle of 45 degree, which is more than the critical angle for glass, and by instead of passing by it, they will again show total internal reflection and get reflected like this. But now at these points, the ray is normal to the plane, and that's why it go undeviated. So we get an inverted image of AB as A dash B dash by 180 degrees. So we can invert an image by 180 degree using this totally reflecting prism. Now the third use is we can invert an image even without deviation of rays. So we can also invert an image without deviation of rays, and this is called erecting prism, right? Erecting prism help us to invert an image without deviation of rays. So here we can see that rays are going like this, and they are incident on the face. I'm naming it as PQR, then this is the face PQ. So the rays are incident on the face PQ of the prism, enter the prism and get deviated, they show refraction. But when they are incident at the face QR, now here they show an angle greater than critical angle, that is 42 degree for glass. So that's why at the point here X and Y, these rays are showing total internal reflection, that is TIR. Again, when they are incident on the PR surface, they get out of the prism since the angle is not greater than critical angle, and when they come out, they give us an inverted image A dash B dash of the object. So at point X and Y, they are giving us total internal reflection. The reason is that this angle is 45 degree, and that's why the angle of incidence is more than the critical angle, and that's how it works. So these are the advantages of totally reflecting prism, or the applications of this totally reflecting prism. The advantage of using this prism as an inverter of image instead of plane mirror is that there is no loss of intensity in the case of prism. Okay, in case of plane mirrors there is always some loss of intensity, while in case of prism they get totally reflected, light get totally reflected. So the advantage of this prism over plane mirror is that no intensity loss in the case of prism, while there is some loss in case of plane mirrors. Now the next or the fourth application of TIR is optical fiber. Now optical fibers are used mainly in communication purposes. So these optical fibers are special kind of wires. We can say that these are special kind of wires, and their working is based on the phenomena of total internal reflection. So I am summing up in points. Like first thing is they work on the phenomena of TIR, first thing. Second thing, these are special kind of wires or cables which can be defined as a hair thin long strand. Okay, hair like thin and long strand of quality glass or quartz. It can be of glass or of quartz, surrounded by a glass coating. The actual wire is surrounded by a glass coating of slightly lower refractive index. And their main use is to guide optical signals from one place to another. Since they guide signals, that's why these are used in communication purposes. So the main use is to guide optical signals from one point to another. Now as we can see the structure, the optical fiber consists of three main parts: core, cladding and buffer coating. We can see here, right? So core is the central cylindrical region which is made of high quality glass. It can be glass, it can be silica or plastic of some refractive index mu1, and its diameter is about 10 to 100 micrometers. Okay, the diameter is about 10 to 100 micrometers. This is the range of its diameter, and it is made up of high quality glass, either glass or silica or plastic with some refractive index mu1. This is the central region, we know it as core. After it, the core is surrounded by a glass or plastic jacket of refractive index mu2. So this core is again coated by a jacket kind structure. It can be of glass or plastic and have refractive index mu2 such that mu2 is less than mu1. ये हमें ध्यान रखना है. The material that we use for cladding has refractive index lower than that of the material in core. This is our main part of the wire, but on above it, for the protection or for providing safety and strength, the core and cladding of these optical fibers is further enclosed in a plastic jacket. So this buffer coating is a plastic jacket to protect the wire as well as to ensure safety and strength. We use this jacket, and this is known as buffer coating. Now their main motive is to propagate signals from one point to another, and they do this work by the phenomena of total internal reflection. This we can show in a diagram. So if we want to propagate a signal from end 1 to end 2, we incident it to one end of the fiber and it is incident to the surface. Now this is cladding. This is the cladding region with refractive index mu2, and this is core with refractive index mu1, and we know that mu2 is less than mu1. That means light is passing from denser to rarer medium. Now we choose incident angle such that it is more than the critical angle of these two materials, the combination of these two medium. So when this angle is more than the critical angle for this particular combination, light, instead of passing to the cladding, it come back to the same medium or to the same core region and will move forward. Similar process take place here. The incident angle will be more than the critical angle, and instead of passing to the cladding region, light go back and get reflected. This is called total internal reflection, and the phenomena continue till the other end. Now if the wire is bended, then also this process is possible in the similar manner. There is no loss, nothing. So we can use these cables to transfer optical signals from one point to another by the help of total internal reflection. Now this is a single wire, but we use it as a bundle of wires, and then the bundle of optical fibers are called as a light pipe. So when there is a number of wires or optical fibers, we call it as light pipe. Light pipe is the bundle of optical fibers, right? So the bundle of optical fiber is called light pipe, and it works on the principle of TIR. Now the applications, they can be used in transmitting and receiving electrical signals in telecommunication, telephones basically. They are used for transmitting optical signals and two-dimensional pictures sometimes. These are also used in refractometers, as well as they are used in medical and optical examination, right? Optical fibers we can use to transmit information to recording information for medical and optical examination. So these are all the applications of these optical fibers. They are constructed into three sections actually. Core and cladding are the major part, and there is a coating for protection, safety and strength called buffer coating, and this whole setup is called optical fiber, which is an application of total internal reflection because it is based on the phenomena of TIR. That's all for the video.